In this problem, we're going to compare compound A, which is shown in a Fischer projection, to these 6 other representations and try to figure out the relationship between each of these and compound A. Just a couple of things to recognize. First is that since we are dealing with a Fischer projection, remember the definition of the Fischer projection. By definition, all vertical bonds on the Fischer projection are pointed away from you. So let me just redraw it. Here's our Fischer projection. By definition, these vertical bonds are dashes because they're pointed away from us, the viewer. All of the vertical bonds. And the horizontal bonds, these are wedges because they're pointed towards us. Now, in this particular molecule, if we look at either of these carbons, let's look at this one on top, we have a CH3 attached, an OH attached, a hydrogen attached, and this carbon here. There's 4 different groups attached, therefore it is a chiral center. And the same thing at the bottom, we do have another chiral center. But what you want to be aware of is that there is this plane of symmetry that cuts this in half. That symmetry makes it achiral. And it's a meso compound. If it's achiral, it does not have an enantiomer. Does not have an enantiomer. So that immediately rules out any of these 6 compounds being the enantiomer of this one. Even if it ends up being the mirror image, it's just the same thing. Now this particular problem is actually easiest to work using molecular models, so that's what we're going to do. The first thing we want to take a look at is compound A and its molecular model. Here's the molecular model for compound A in the Fischer projection form. We can see that if we kind of look at the side here, we can see here's our 4-carbon chain, our top CH3 group, our bottom CH3 group. But if we're looking at this in terms of the Fischer projection, you can see if we look at it in this direction, we have on the right, on this top chiral center, the OH. On the left, the hydrogen. On the bottom chiral center, the OH on the right, hydrogen on the left. And if we kind of look at it like this, you can see where you can cut this right down the middle, and you have that plane of symmetry. So here's compound A. We'll set it aside. Now let's get a model of our first structure here. Okay, here we have our first structure, our main backbone. We have our CH3 group, which is this carbon. Then we have our next carbon, carbon, and OH. Carbon, carbon, OH. On the carbon on the right, we have this OH pointed out towards us, the hydrogen back away from us. On the carbon on the left, we have the carbon pointed towards us. Now, if we compare these two, notice in our original molecule that the OHs are on 2 different carbons. In this first structure, the OHs are on the same carbon. So the atom connectivity is different here. That means these two represent constitutional isomers. Okay, so the next one we want to look at is the second molecule over. It's another 3D representation. And notice now that we do have the OHs on two different carbon atoms. So let's build the model of this one. Okay, so here we have it. You can see that our planar groups, we have the hydrogen, carbon, carbon, and hydrogen, which is exactly what we have in our structure here. We have the OHs pointed out towards us, and then the two carbon groups pointed back away from us. Now, what we want to do is manipulate this to see if we can get it to somehow match our compound A. Now, what you might be tempted to do is just set this up like this, and we see that we do have mirror image structures here. They are mirror images of one another. And that might tempt you to want to say, well, these two must be enantiomers. But remember the first thing we said, since compound A is achiral, it does not have an enantiomer. In fact, in this case, the mirror image is just an identical structure. And if I flip this over, you can see that these two are the exact same things. They're superimposable. All the atoms line up. They'll superimpose right on top of one another. For that reason, we classify this molecule as identical to compound A. All right, let's look at the third one. Again, the best thing you can probably do is build a model. Okay, here we have our model of this, and in the plane groups we have OH, carbon, carbon, OH, which is the same thing. In our molecular model, we have our OH, carbon, carbon, OH in the plane. We have one CH3 coming out towards us, kind of at the bottom, and the hydrogen back. We have the other CH3 up, but coming out towards us. Now, for this, if we want to essentially do this as a Fischer projection, what we want is kind of to match this one, to have our 4-carbon chain in this sort of pseudo-cyclic orientation. So let's take this model and rotate this so that our carbon backbones are the same to have a Fischer projection. Now let's look at this from the front. Okay, now we have a second Fischer projection here. In fact, we can even draw the Fischer projection of this one based on this model. So let's do that. Okay, we'll start with our CH3 right here. Okay, then we have our carbon with an OH on the left, hydrogen on the right. Then on our next carbon down, we have a hydrogen on the left, OH on the right. And then finally, we have to put in our CH3 group, which is kind of here in the back. There's our Fischer projection. Here's our chiral centers. Now this Fischer projection no longer has a plane of symmetry here because the OHs aren't on the same side. This particular molecule is actually chiral. Okay, so the difference in it and compound A, the first chiral center is swapped, the second chiral center is the same. So these two, they're not mirror images, they're not superimposable, so they're diastereomers. All right, let's look at the next molecule. We are given a Fischer projection now. Okay, and if you want to make the Fischer projection of this in a model, we have this. Okay, so again, our main carbon backbone is in this almost pseudo-cyclic orientation, because if you're looking at it from this direction, you want these vertical bonds to be pointed away from you, the viewer. So that way, if we're looking at it like this, all of these vertical bonds, the carbons, are all pointed away from you. Okay, so here is our Fischer projection. And we have at the top chiral center, the OH is on the left, and we have it on the left. Bottom chiral center, OH is on the right, we have it on the right. Now, if we compare these two models, they're certainly not mirror images of one another, because we have on this first one the two OHs on the right. And there's no way, even if you try to twist this around, you might make the OHs match up, but now you don't have a mirror image between this hydrogen, and on the other one you end up with a carbon. So there's no way that you'll ever get these to superimpose either. So for that reason, they're non-superimposable, they're not mirror images, they must be diastereomers. This next one is very similar to one we saw on the top, except now we're given a Fischer projection. Okay, and what I did, we still have compound A, we have its Fischer projection. Now for this compound, I built the Fischer projection of it. Okay, so we're looking along here. Here's our two chiral centers. At both chiral centers, the OH is on the left. Now again, this can be a little bit tricky because these are mirror image structures. You see the mirror image there. But you can't say they're enantiomers because remember, A is achiral, it doesn't have an enantiomer. So its mirror image is actually superimposable on itself. So if we flip it over, now we have this superimposable structure where everything lines up and they'll superimpose. So this compound is identical to A. Okay, our last structure I think best illustrates the usefulness of molecular models in doing these. So we're given a Newman projection, and I actually built the model here of the Newman projection. You can see that here's our front carbon of the Newman, which is this front carbon here, coming up we have the methyl group, down to the right, the OH, and to the left, the hydrogen. Then on the back carbon, which is right here, on the back carbon we have the methyl group up and to the right, we have the hydrogen up and to the left, and then the OH group down. Okay, so it's a little hard to get the best viewing perspective here. But if you look at it like this, you can kind of see the Newman projection structure. Now, what we want to do is try to compare that to the original model. Okay, so let's set it up on its side. And remember, in this Fischer projection, my carbon backbone I have twisted around in that pseudo-cyclic pattern. Let's do that with our Newman projection, because we've now taken it from here. I'm going to set it up on its side, and let's twist these carbons around to get that same orientation. Now, if we look at this, we can flip it around a little bit. Now we've turned that into a Fischer projection. Okay, again, be careful. It looks like the mirror image of the original compound, but if I manipulate it just a bit, you can see that it's the identical structure. So this Newman projection is identical to compound A. So these examples just go to show how using molecular models can sometimes be the easiest way to figure out the relationships between different compounds.